Okay, for this problem, we're given a function. Here it's secant x, and we're first going to find the second degree, n is equal to 2, Taylor polynomial of secant x centered at 0. Then we want to use Taylor's inequality to estimate the largest possible error being the difference between the value we get from the Taylor polynomial and the value we would get from the actual function, the maximum possible error if we're limiting the x inputs to this range here. And then the last thing we're going to do is graph the actual error, so the actual difference between secant x and the Taylor polynomial, and see how the actual error compares to what we got with Taylor's inequality. Now, we're going to work a bunch of example problems just like this in the upcoming videos. However, I wanted to do this example first because it addresses an issue regarding the application of Taylor's inequality. So in this particular example, it ends up being the case that the Taylor series of secant x centered at 0, so to create the Taylor polynomial, we're going to be pulling from terms from the start of the Taylor series of secant x, right? So the Taylor series of secant x centered at 0, the Maclaurin series of secant x, is one of the cases where, like every other term, is a 0 term. We saw this, I think, with cosine x and sine x. Sometimes this happens. Okay, it's not a big deal. However, as we saw in the text, when we went through the textbook, this does create some confusion on how exactly you're supposed to apply Taylor's inequality. And based on what the example the textbook showed, if we take a look here, here's the example. So it's the first, it's the t sub 5 of the Maclaurin series of sine x. And what they did was, like every other term is 0, right? So they're skipping x to the 4th, x to the 6th. And when they applied Taylor's inequality, you can see they didn't use, so this is t sub 5, right? It's the 5th order Taylor polynomial. So you think, okay, well, I guess that would mean we might plug in n is equal to 5 into Taylor's inequality and get the r sub 5, right? That's what we always do. We plug in, it's the function is equal to the Taylor series. The full infinite series is equal to t sub n of x plus r sub n of x. So we plug in, here it's t sub 5, and so we would plug in n is equal to 5 into the Taylor's inequality. And yeah, that's exactly what you do for most problems. If there's the only confusion is when you have 0 terms. There's confusion comes up. If there's no 0 terms, then that's exactly what you do. And so, but with these 0 terms, it was a question, well, do you still do that? And you can see here, that's not what they did. They plugged in n is equal to 6 to get r sub 6, right? Here's the n plus 1th derivative, the 7th derivative. And so my assumption was that, well, the reason why they did that is because they didn't want to be evaluating a derivative in Taylor's inequality that was associated with a 0 term, right? Because there is no 6th derivative term here. So to me, my conclusion was that, well, that's the standard procedure. However, when I worked this example problem that way, got the answer, checked the back of the book, and saw that the answer in the back of the textbook for this problem is based on using the method of plugging r sub 5, n is equal to 5, into Taylor's inequality. And it doesn't matter that you're looking at the n plus 1th derivative that's associated with a 0 term with Taylor's inequality. It doesn't matter. So, you know, to me that's pretty confusing. I don't know what they're showing here. My guess would be that, you know, if we assume the answer in the back of the book is correct, then, which, you know, it should be, the authors put it, then what's going on here is that they did a comparison to start off with. They estimated the error using the alternating series error estimation theorem. That's what they started with. And with that theorem, you use the next non-zero term. It's the absolute value of the first non-zero term that you didn't use in the partial sum, the Taylor polynomial. That's what the error estimate is based on. And so we got that using the alternating series error estimation theorem, and then they wanted to compare. They said, what if we use Taylor's inequality instead of the alternating series estimation theorem? And to compare that to what we got with the alternating series estimation theorem, you needed to use that the corresponding seventh derivative term. So for comparison, they did it this way, but it's still pretty confusing to me. Like, why not give us a note, you know, saying, well, look, in normal situations, you don't do it this way. So I don't know. I'm trying to talk to some mathematicians to get an answer on this, but you're welcome to do your own research. I'm just going to go by what's in the back of the book. So what we're going to do in this example problem and any other example problems that involve zero terms is we're just going to plug the n of the Taylor polynomial straight into Taylor's inequality, and not worry about if the derivative we're using to get the capital M and all that is associated with a zero term. We're not going to worry about all that. So, okay, so first we want to get the Taylor polynomial, so with n equal to 2. So to do this, we go through the same process that we would normally go through to build the Taylor series. So we make two columns, and in this column we're going to put the function and its derivatives. Okay. So that's tangent x times secant x. Okay. Let's do the second derivative. Secant. Okay, so that we can see is, so sine squared x over cosine cubed x is going to be tangent squared x times secant squared x. So, okay. And then plus secant cubed x. All right. So that will be enough to get us to the second derivative. We're just going up to the x minus a squared term. However, we want to go one derivative past that because for Taylor's inequality. Now, you know, if we were going actually to we wanted to go to the next non-zero term, because what's going to happen is, if let's go ahead and plug the center point in. So we come to the right hand side column and we plug the center point in. Center point is 0, so secant of 0 is 1, and then tangent of 0 is 0. So you can see here this is 0, and then this is going to be 1. So every odd n value, because the n is associated with the derivative, right? Here's the 0th derivative, the first, second. So every odd n, which corresponds to the power, right? This is going to be x minus a to the first. That is going to be a 0 term. So this would be associated, f triple prime of 0 is going to be 0. And so if we were going to be applying Taylor's inequality with a non-zero term, making sure that the derivative is associated with a non-zero term, then we would take the third derivative and then go to the fourth derivative. But we're not going to do that. The answer in the back of the book doesn't do it that way. All they do is just, so they get the third derivative. So this doesn't matter. So, okay. With respect to x, the third derivative, okay, and so this is, so you got 2 sine x cosine squared x over cosine of the fourth of x. So that's 2 sine x over cosine squared x. which is 2 secant x tangent x. So, okay. All right, and then, so 3 sine cubed x over cosine of the fourth of x, that's 3 secant x tangent cubed x. Okay, and then plus, it's going to be 3 sine x over cosine of the fourth of x, so that's 3 secant cubed x tangent x. Okay, now again, we're not plugging. You can see if we plugged in 0, all the tangents go to 0. There's no need to plug in the center point with Taylor's inequality, and maybe that's why you don't have to worry about a 0 term. The 0 term only comes into play when you're plugging in the center point, and that's not really what we do with Taylor's inequality. So, but yeah, so next what we want to do is, so we've got f of 0 is equal to 1, and then f double prime of 0 is equal to 1. Okay, and you know, it doesn't matter. It's not like n corresponds to how many terms you use. It just, you sum the first non-zero terms up to the order of n. This is going to get us to the to the x squared term. So, okay, we know that c sub n of the Taylor series is the nth derivative evaluated at the center point over n factorial. Okay, so this here, these two, this is the nth derivative at the center point. So to get the c sub n for each of these, the coefficient, we just divide this by n factorial. So this is divided by 0 factorial, which is 1. This is divided by 2 factorial, which is, so that's 1/2. Okay, so now there we go. So now we can go ahead and write the Taylor polynomial. So we've got the function secant x is approximately equal to, we're approximating the function secant x with the second degree Taylor polynomial of secant x, which is, so the first term is, the coefficient is 1 times x minus a to the 0, so it's just 1. Second term is, the coefficient is 1/2, and then x minus a is 0, x squared. And that's it. Okay, you know, and just to point out, I mean, you know, I don't know if you could ever get a situation like this, but let's say we were doing t sub 10. And for some reason, I don't even think this is possible, but for some reason, like the first term was 1, but then the next 9 terms or 10 terms were 0, and then the next non-zero term was something with x to the 10th. So you just had 2 terms. That would be t sub 10. Just 1 plus the term with the x to the 10th. So it's all about it's confusing because when we saw with like partial sums, it was pretty much like you're summing the first n terms. Pretty much, I say pretty much because I guess if the series started at n is equal to 0, then it's technically, if you had s sub 5, you're summing the first 6 terms, but you think about it that way, like you're summing the first whatever terms of it's close to, it's either exactly that or it's very close to you thinking about it that way. That's what s sub n means. But with Taylor polynomial, it's really not, it's really this n here. Yeah, it's a partial sum, but it's more, it is a partial sum. You're summing a certain number of terms. It represents, you're summing a certain number of terms of the Taylor series, of initial number of terms, but the n is more about the order. Okay, so, all right, next we want to estimate what is the maximum possible error. We're going to use Taylor's inequality to get what is if you're going to input an x into the Taylor polynomial here that's within this range, then what is the maximum possible error you could get meaning the biggest possible difference between the value you got using the Taylor's inequality, or no, using the Taylor polynomial, and the value that the function would give you if you plug that same value into the function. So there's Taylor's inequality, and it's all about, so this is what we're doing here is we've got the function is equal to the Taylor series, right? The infinite Taylor series. And this is equal to t sub n of x, but we're at t sub 2 plus r sub 2 of x, right? That's it. We've got the t sub 2, this, but then the actual function, though, is this plus everything else we didn't. This R2 represents everything else that's not included in the Taylor polynomial in regards to the infinite series. What we want is an estimate on what's the biggest this could possibly be. And so, according to the answer in the back of the book, all we're going to do is just plug we're trying to get R sub 2 here, right? This gives us, this is what we want here. This is exactly what we want. This is an upper limit on the R sub n, but we're going to plug in 2 in this case. This is what we're looking for. And based on the answer in the back of the book, we're not going to think about, well, okay, we're going to have to use Taylor's inequality, we're going to have to use the n plus 1th derivative, which would give us a 0 term in the Taylor series, right? There is no x cubed term. That's a 0 term, but we're going to be using the x cubed or the third derivative. We don't worry about any of that. We're just going to, no matter what, in general, we're going to plug, if we're doing it, whatever the n of our Taylor polynomial is, we're going to plug that same n into Taylor's inequality no matter what. All right, so if you look here, so this is what we want. This is what Taylor's inequality is going to give us. But if you look at the value, the upper bound, well, we already have n. We chose n. We already have a. We picked a. Okay, and we know d as well. So you can apply this Taylor's inequality, this upper bound on R sub n. It can be applied for all real numbers, like any x away from the center point. You could apply it that way, or you could, if you want to, you could restrict it to a certain distance away from the center point. And that's what we're doing here. The d in this case is 0.2, right? The farthest you could be above or below the center point is 0.2. So we have d, we have n, we have a. Taylor's inequality is all about this capital M. We need to find the capital M. How do we do that? Well, it tells us right here. We need to look at the function, which is based on the n plus 1th derivative of, in this case, secant x. So that's the third derivative. So what is the absolute value of f prime of x? Well, we just did that. 2 secant x tangent x plus 3 secant x tangent cubed x plus 3 secant cubed x tangent x. Okay, so this function here, the absolute value of the f triple prime of x, is this less than or equal to some number n so a is 0, the absolute value of x is less than or equal to 0.2, right? That's exactly, these mean the exact same thing. Okay, well, how do we answer this question? Well, it sounds complicated, but this is just asking us what is the absolute or the global maximum of this function over this interval. That's all it's asking. We worked a bunch of global maximum problems in chapter 4. So let me type this function here into Desmos. Okay, so there it is, the absolute value of the third derivative of secant x. And it looks almost like these look like straight lines. I mean, you can see they're curved. We're really zoomed in to around plus or minus 0.2. But there you go. We can see that it's at the endpoints. Maybe the endpoints are the same value, but one of the endpoints is going to be the max value, right? So at the endpoints, then no matter what x you plug in, it's gonna be one of the two endpoints, or it could be, or maybe they're both the same value, but no matter what x you plug in into the absolute value of the third derivative of secant x, we can get a value m that no matter what, any x, you'll never get a value out of that function that's greater than m. Okay, so let's see, there it is. So let's store that as, we'll call that d for derivative. Okay, so we're in radians. So, okay, d with x is equal to 0.2. Okay, now let's just check the other endpoint to make sure maybe they're different. No, they're not. So 1.08516, that's m. Okay, so there we go. We've got m. Now we have what we want. We can say that, so r sub 2 of x, the absolute value, is less than or equal to, and so now we plugged in n is equal to 2, so just, we've got n plus 1, that's 3 factorial, and then, okay, and then the absolute value of x to the third, okay, and this is for the, well, let me do this first. Okay, well, so there it is. 3 factorial is 6, so this divided by 6, 0.18086. So okay, now this is for the absolute value of x is less than or equal to 0.2. Okay, so there it is. We've got r sub 2, but it depends on the x value you choose that you're evaluating the function at. And the Taylor polynomial, it depends on the x value, but it's any x value from minus 0.2 to 0.2. But if we want to answer the question that no matter what x value we plug in, what's the largest that r sub 2 of x will be, no matter what x value you plug in, then let's just pick the x that makes this term the largest, which for every case is just going to be the farthest away from the center point. Now, you might be wondering, well, don't we have to pick the same value that we used to get m, which in this case actually is all the way the farthest from the center point? But that won't be the case every time. M could be, we could have, let's come back here. We could have, there might be another case where they're the endpoints and you got something like this or something. So maybe the capital M is up here away from the endpoints. Okay, so does that mean that we have to choose that x here, that middle, that's not the endpoints? No, those are two independent processes. One, you're determining what capital M is, and then here you're just saying, okay, I can plug, here's r sub 2 of x, I can plug any x I want in the interval there. Well, what's the worst case scenario, right? So, and here it's always, just because of the formula, it's always going to be just put the radius of the radius, this radius. So, okay, 0.2 cubed, and it's the absolute value, so it doesn't matter if you use the plus or minus 0.2 or 0.2. Okay, then times this, 0.00145. So there we go. There it is. If you, with this t sub 2 approximation for secant x around 0, if we're restricting the x's we can plug into this interval, then the worst that this is going to be off, from the actual value of the function is 0.00145. Now you might be wondering, well, wait a minute, didn't we choose x to be 0.2? Isn't this r sub 2 of 0.2? No. This is R sub 2 of x. We're just answering the question. We're answering the question that we were asked at the beginning. What is the absolute value of R sub 2 of x? We can plug in any x we want. What is the largest that the magnitude of that could possibly be? No matter what x you plug in, as long as it's between minus 0.2 and 0.2, no matter what x you plug into R sub 2 of x, the absolute value of that is never going to be bigger than this. Okay, so now the last thing we want to do is let's graph the actual R sub 2 of x. You might say, well, how can we do that? Well, because we know the absolute value of R sub 2 of x is what? It's the absolute value of the function minus the t sub 2 of x. So it's going to be minus 1 minus 1/2 x squared. Now you might be wondering, well, wait a minute, then what was the point of Taylor's inequality? Why didn't we just use this? Well, yeah, in practice, I guess if it's not that, you would do this. Why not? But these problems are just for illustration of how to apply Taylor. We're just analyzing Taylor's inequality and the whole Taylor polynomial. In practice, maybe you don't have the function, or maybe this is too difficult. It depends. Okay, so there it is. There's the absolute value of R sub n of x. And you can see I zoomed in on minus 0.2 to 0.2, so the endpoints are the worst case scenario, and that looks to be both are about the same, and that's about at, so 1, 2, 3, 4, 5, so each tick is 0.00002, so this is maybe 0.00034 or 35, and Taylor's inequality gave us 0.00145, so that's still not bad. I mean, we're going to see other examples where Taylor's inequality does a lot better, but that just gives you a sense of what Taylor's inequality is, how it performs. Okay, so I will see you guys in the next video.